Welcome to the Highway Tech Show, where we focus on insights and strategies and solve some of the top challenges in highway tech, reconstruction, and accidents with trucks, bikes, motorcycles, and more. Let's get started with the show.
John Grindey here.
And John Steiner here.
We are the hosts of Highway Tech. We talk with the top leaders of OEMs, commercial fleets, legal, and much, much more on this show.
And we're excited to have Dr. Jeremy Weiss here of Rise 25, who has done thousands of interviews with successful CEOs and other business leaders. And we're going to flip the script. So, you know, what we've talked about, we're going to be having great guests here. But today, Dr. Weiss is going to be interviewing us.
Thanks for having me, Steiner and Grindey. And, you know, I'm excited because we're going to talk about the evolution of Reconstruction and some of the innovations. And you're going to walk us through some examples of some of the amazing things you've been able to reconstruct. And before we get into it, this episode is brought to you by MecanicaCorp. And I know MecanicaCorp, you guys have decades and decades of experience providing engineering and scientific analysis services to many industries: legal, automotive, commercial truck, bus manufacturing, transportation, and more. I guess you guys like to say it, and I think of it in this way, is if it has wheels and rolls down the highway, I guess, or a golf course, right, then you have their back. So anything from golf carts to passenger vehicles to heavy truck and bus, you guys take care of it. And I know you utilize cutting edge tools, and that's what this episode is going to be about, to where we were and now where we are, because a lot of times the people who can innovate the best and the quickest have seen everything. And so they know what to do. And so you utilize these technologies and methodologies not only to perform accident reconstruction, analyze crashes, but also to communicate that analysis clearly and quickly to your clients. And I know anywhere from highway vehicle safety research, testing, collision analysis, expert testimony. I love the term black box data that you guys do too. So if you have questions, you can go to MecanicaCorp.com and contact them and their team and about their services. So let's start off. Take me back in the day. What did reconstruction look like then?
Back in the 80s, I'm really dating myself. He's a lot younger, but we did things by hand. All the drawings were done on draftsman tables and developed with pencils and French curves and scale rulers. And you'd have to go to court and you would roll out a 12-foot, long drawing and explain everything in court with these hand-drawn things. We'd end up using acetate to cut out little cars to draw them as the dynamics to show how, or a flip chart. You would take flip charts and you kind of do the old school, like when you were a kid and you took your, and you go and flip through to kind of have the motion go down, and you'd stage it out. That was how it was done, because as this was developing, tools like AutoCAD, which is the big manufacturer for the CAD drawing stuff, those were just starting to come into play. So basically what we did was we went from fiber tapes to steel tapes, and those are tape measures. Then what everybody has in their kit, probably to this day, is a roll of tape. I think every reconstructionist who doesn't have a roll of tape's running a little short on themselves. And then it moved on to a total station, where we would go out and map the scene with a total station. Then it evolved. The equipment got better, and they started coming out with scanners. The initial scanners were
big,
huge, large, heavy. They were 45 pounds. You had to lug up high. You had to reset them every time you moved them. It took forever to do. And now they're the size of the old boom box. So you have a little itty bitty,
like a little projector
size tool, sits on a tripod. You plug it away and away it goes. And then you move it and the way it keeps going. So it's a lot more efficient. And
how many guys did it take you to get that big Leica scanner?
Well, one for me. It'd take you probably 3.
But when you power lift in the morning,
that was nothing.
He power lifted first gen 3D scanners.
First generation 3D scanners all over the place.
So what do the scanners do?
They're a laser. They're lasers. So what they do is they scan the entire thing by either time of flight or phase shift lasers, and it loops around the entire scene 360 degrees from wherever it's set up, and you catch every piece of evidence out there or everything that's on that side. It does leave holes, so you have to move it around. So like on a car.
So Grindey mentioned this the intermediate piece of technology, which was great, which was the total station. But you had to manually, the ones we use, you had to manually sight it. So you're looking through the machine and you see, let's say you see a tire mark or what some people call a skid mark, and it's curving. Well, when you bring that data back to the office, you need points on that skid mark so that you can draw it on a drawing. So you would take points maybe on each side of it if it had some thickness to it. And then picture basically the CAD guys back at the office would take your points you shot, right? And then connect them all. It's like connect the dots, and you would start drawing out. There would be dots that would define, the striping and the roadway edges. Where are the sidewalks? Where's the center island? Where are the skid marks? Now with the 3D scanner, what Grindey was talking about, now you just deploy this thing, stick it out there,
let it rip.
It spins around, and it just, where you were manually shooting the points you wanted, this thing is just getting everything.
And it captures what's great about the scanners is it starts to capture the undulations, or let's say there's a pothole and it becomes an issue in a crash. You don't have to just mark out that pothole and try to measure it with a total station. You just scan it and it develops the hole that was there. It sees it, and you're able to capture that hole, model that hole, and then determine whether or not the suspension was this a cause of the crash, or was this not a cause of the crash? Does something help?
Go further back. How did we used to do it with a scale across
and
then
the top
and then a tape measure to get the depth of the thing in a couple of different points?
Yeah.
And
I digress a little bit. Years ago, when you had an accident, you would use a crush analysis. So you had what was called a crush jig. I don't think we even have one anymore.
I don't know where
there. You set up basically a series of rods to where the damage is on the car, and you'd measure it out, and then you would take a plumb bob and measure it out, and then you would draw it and calculate how much depth that went in to cause that. How much force would it take to crush that car? That's what it really gets to. Nowadays, you scan it exemplar, the exact exemplar. You put them in the program, you flip them, and you go, here's my crush profile. How much damage is there? And then you do your calculations from that. It's much quicker. It's much cleaner. It looks really nice, especially in front of a jury. The juries love that stuff, It's the CSI effect, of course.
When I first started, and Grindey's been doing this a lot longer than I have. When I first started in 1999, I came in just on the tail end of the end of the old-fashioned way to do it. So I had a year or two, maybe a little more of, roller tapes and tape measures and plumb bobs and crush jigs. But you learned a lot that way. I mean, it was a lot.
When you do it manually, you learn a ton.
Yeah. Oh, there's no question.
It forces you to slow down because you can't go fast. Now these kids, the kids, and I'm calling them all kids, the younger engineers we have, it's like, it's not fast enough, some of the stuff they're doing. That's how it's developed. We've developed into a society of super fast. We want it now. And it's not fast enough. And they're like, this thing's taking forever to do it. Oh, no, wait, let me show you forever. You'd be out for hours doing stuff.
Yeah.
So they're upset if they spend 2 hours at a car, and we're like, I used to spend a day at a car. It took forever to do.
But now it's transition, though. There's still a lot of work to do. You can get the field work done fast with these new technologies. Absolutely. But what you've done is you've just transitioned the work. Because now you got to do something with all that data you collected, right? And so now that transition is now done back at the office. It's just quicker to get the inspections done, but there's still a lot of work to do, and it's just now done back at the office.
Let's talk about some of the innovations on site, and then we could talk about some of the innovations back in the office. And because I noticed, Grindey, over your head, if someone's watching the video, there's a drone. What are some of the other things lately that you're able to use in your work compared to before?
Well, I'll move my head this way because I'm backwards looking at my screen. Sorry. Those types of drones now capture an immense amount of data because it is a high grade camera that is taking a photograph from a couple hundred feet directly above, or an oblique angle,
or less if
or
restricted
less
by the FAA.
I will claim that I'm not an FAA 107 pilot.
Neither am I.
We have everybody here that is.
Yeah.
That we have most of the crew.
Yeah.
That most our team is our pilots.
Yeah.
So they're actually certified by the FAA to fly drones.
And we have a chief pilot, and then
Wow.
a couple other engineers that are licensed pilots, and they have their own workflow, and they have their regular meetings to stay current with regulatory changes put out by the FAA, so that we make sure we're in compliance with these drones.
That's pretty cool.
And they actually have there's some airspace areas where you have to get approval by the FAA. They've done that to get so we can fly the drone and manage it. The drone combined with the scanning is really high level because you have not only ground laser data, you have aerial data to put on top of it. And the model that gets generated is exactly how it was at the time of the, right near the time of the crash or just after the crash. A lot of times, we've had cases where they come in, 2 years ago, the crash happened. Well, the road really hasn't changed. If the road hasn't changed in 2 years and they've expanded it, the road's pretty much the same. So you can go out, do these kind of data analysis. Then you go back and take the photographs that were taken at the time of the crash and model through Photo Modeler, through some of these other Synthesize and some of these other programs that we have that have been developed to look at specifically videos, photographs. You put them in and it will now determine where it is. Photo modeling's been around for a while because that's how in the old days you'd get a picture that was 2 years old and you would try to figure out points in space on that picture, match it to where your actual data is, and
that was all
that was all hand
35 millimeter film in hand. And one of our mentors, who unfortunately passed away a couple of years ago, but John Kirchhoff was big on this, and we actually, his wife had donated his library, and we have a lot of his old work, and it's amazing how labor intensive it was then, and how it's progressed to these new technologies that allow you to do it in the computer. It's unbelievable the stuff you can do.
I want to talk about the cutting edge stuff. If there's any other things to mention on the cutting edge on capturing the data, and then I want to transition to back office. Now you have all this data. What do you do with it?
A fire hydrant.
Control the flow. Yeah,
it is.
It is an absolute fire hydrant. There is so much data. We're actually we're running out of server space. That's how much data comes in. The cameras, back when we did 35 millimeter film, right? You just kept the rolls of film, you produced them, kept the negatives. You could reproduce them later. You can blow them up. Now it's all digital. Most of the digitals, because we shoot both RAW and JPEG, so we have an actual RAW file we can use. They're massive amounts of data. So we're taking up a ton of space. And the drones, same thing. It's a massive amount of data. The Pharaoh is a massive amount of data. Yeah. Manipulating that data, it's almost as if you don't have a computer that's within 2 years old, you're done. You cannot manipulate this stuff on older computers. It takes too much power, too much RAM, and there's just not enough horsepower in the computer to make sure these things are being processed.
Yeah. So we use ProLine cameras, and there's always a fun little thing going on amongst the team. So I'm a Canon guy, and I shoot a Canon 5D, which is a very high-end camera, not as fancy as a 1D. This guy over here is on the Team Nikon. whatever.
Nikon.
And so, but you know, the Nikon, I mean, that's beautiful stuff, right?
D5.
I mean, you know, I would say, you know, Nikon's like Porsche and Canon is like Mercedes, you know, a little more refined.
Canon's great for video. Nikon's better for photos.
But well,
That's the argument.
we'll see. So, but anyways, they're both great cameras, and it's just kind of what you're used to. And but Grindey talked about something important that, you know, something we have to maintain for the clients in the cases is all of this work product that we develop.
Mm-hmm.
And you go do a scene inspection, you come back with 5, 6, 7, 800 photos. And they're, you know, with these Proline cameras, those photos are like, I don't know, 11, 15, what are they, megs big, 11,
They're
15? And then you get RAW, they get even bigger.
Yeah.
Times, you know, 500. It's a lot of data.
Yeah. Well, the end result. So let's, you know, back in the day, flip charts. What does that look like now?
So the flip charts where you'd have you know, well, we've got a great example over here from a big case from 35 years ago, where you have think of, so the trial exhibits used to be mounted on foam core, right? Poster, you'd buy these big HP plotters, these old school plotters, and you'd print things 30 by 40. So picture in a drawing, right, of the accident scene, top-down view, and you'd have these acetate pages where now you want to show where the vehicle came to rest, and so you flip down your first acetate, and it had the in scale where the vehicle came to rest. Then you want to know where it was each second prior, and so you flip down these flip charts. Now, you know, with you know, it's basically PowerPoint. That's been replaced by AutoCAD. So all your scale diagrams are in AutoCAD, and they're presented in PowerPoint or some flavor of, you know, there's a couple of different things out there. And that's it's all we have these cases. I should have brought one over, these old school cases where you'd walk into court with this big portfolio and it had, you know, all of your trial exhibits in there.
You literally walk into court now with a laptop. That's it.
Yeah. Or a thumb drive.
A thumb drive. And you go here and they plug it in and it shows to the jury. You know, and when I mentioned CSI, you know, earlier, people have seen that, and that's the expectation that the average, you know, most people think that that's how it is. You know, this crash happened. There's all kinds of data on the car they can plug in. It shows a video. We're there. We are literally there. There's video cameras that are in cars now. So all that stuff's there. Now it's putting it all together and showing it to a jury to make sense.
Yeah.
And we're to the point where we're doing animations as well. So we are not only taking all this data, reconstructing the crash, how it actually physically happened through science, right? And you know, all the physics behind it, coming up with the answer, then putting it into several other programs like simulation programs or animation programs, and coming up with, here's what it looks like, and using that in court from the old flip chart to here's actual motion with a time counter on it and stopping at certain points in time along this path.
The one thing that hasn't changed is taking all of this analysis, this physics and engineering based analysis, and laying it out in a concise and efficient way that you can explain to a jury and to non-technical people, you know, a pretty technical topic, but without putting people to sleep and getting to the point. That's the really interesting part. It's a challenge, and arguably it's gotten harder because, you know, of all of these technologies and things that now, I mean, reconstruction used to be, you know, Excel was the complication, and then came some physics-based simulation tools like, you know, the McHenry software and based on the old Crash 3 algorithm. These are analysis tools that were started with, you know, Jeremy, you're probably too young to remember, but when servers had punch cards and you'd throw out your programming and your analysis on punch cards, and you'd have to get it in the queue and wait for it to come in. Yeah. And so
that is before my time. Yes. You know, I want to talk about this specific, so we could put it all together today. specifically of what occurred on Bandini, but I just want to say what pops into my head with this, all of this is with what you do. It's is kind of Disney. I picture the old, if you look at the old animations, they're just hand drawn, flipping through. And now the technology that you use and really Disney uses to create these amazing animations, that's really, in my mind, what I see the equivalent, you know? Yeah. So talk about Bandini. What happened? What?
Bandini. So we're talking Bandini Boulevard, Los Angeles. A lot of trucking terminals, a lot of industrial activities going on there. One very interesting case with a tractor trailer pulling out of an industrial area, out of a driveway. Bandini was 35 mile an hour speed limit, I believe, and driveways, right? You pull up to the apron, you stop, you look. You look for pedestrians, you look for bikes, you look for cars, if you're clear and you can legally pull out, you enter traffic. You may see vehicles that are, some distance away. In a perfect world, in theory, you want to be watching those for a little bit of time so you can understand how quickly or not they're approaching you. But this particular case was a truck that saw a set of headlights. This is at night, way down the road, and from this driver's perspective of coming in and out of this facility on a regular basis, estimated that he had enough time to clear I think it would be, is that the eastbound direction?
Eastbound. Yeah.
To go westbound Bandini. And it turns out he didn't. So as he's pulling out and he's got a 53-foot trailer, this driver, the trailer almost clears, but then the claimant vehicle, the other vehicle, basically drives right into the side of the trailer. Big accident. And rapid response, get a call from the client, very, very early in the morning to go out. Please, let's document the scene, do the usual thing. And this is where we have to watch for new technologies now, right? We have to watch for cameras. Well, the team of engineers that went out saw cameras, quarter mile of the way down the road, half a mile down the road, a mile down the road, and another set of cameras about a mile and a half down the road, and coordinating with other responders to make sure that footage gets secured. That stuff gets saved. Our team does the Faro scanning, the 3D scanning of the scene, documenting the tire marks, documenting the paint marks by the sheriff's department, documenting the vehicle, downloading data from the vehicle, the black boxes, and then tying it all together, and especially the video to understand. Now, if we have video and you see a vehicle cross the screen, and you have a decent distance from one end of the video to the other, and that distance, and you can get a time from the timestamps and the frame counts in the video, miles per hour, right? Distance over time. You've got those two out of the video. You can start using those as analysis. And that was a case that tied in all of these technologies. And in the end, it turns out that this was a vehicle doing between that mile and a half, it was between roughly 60-ish up to almost 70 miles per hour on a 30 or a 35 mile an hour zone.
Yep.
And that was a huge, contributing piece to why this accident happened.
And that's knowing, it started at A and it went through camera A at a certain speed. Then he hit camera B. So the distance between A and B, we know, and you can average that velocity. So there's a multiple sets of velocities. That's why it was ranged between 60 and 70. But it gives you an idea of when the truck driver comes out and says, yeah, he was X amount of feet away. Well, if you
verify that with the science and is what because it's in the end, his word against the other person's word, but not if you have all of your data collection that you use. And it's like, how do you, if you're a car, if there's a 50-foot trailer, how do you slam into it? Right? If you're so far away, well, if you're going the speed limit, if you're not, that's another story. And you could prove that with the data, and that's why people call you. So no, I appreciate you guys walking through lay people like me, and all of this. And if anyone wants to find out more, they check out more episodes of the podcast, check out MecanicaCorp.com to learn more and check out more of their interviews. So thanks, everyone.
Thank you.
Thank you. Thanks.
Thanks for watching and listening to the Highway Tech Show. Take action with what you've gotten today. And if you want to never miss a show, make sure to go to highwaytechshow.com.